Hello, everyone, and thank you for inviting me today. I'm really excited to be here and have the opportunity to talk to all of you about quantum applications, kind of where the status is, and how XPRIZE, which is a nonprofit company running big prizes worldwide, comes into play for quantum computing. So I know we have quite a little bit of time, and as Henry already mentioned, we can, ask questions as we go through this talk. So I will try to divide the talk up and then give you opportunities to call for questions and go from there. So let's get started. I guess my first thing would be I share my screen, making sure I do that correctly here. Okay, so before I go into the talk, I do want to give you a little bit of an outline. So first of all, I just want to open why quantum computing. And as many of you know in the field, you have an idea about why quantum computing, but I pretty much want to make a case regarding what we're looking for in quantum advantage. So quantum advantage is the holy grail of quantum computing. So if quantum computing is not better than classical computing, then we pretty much are not on the right track. So we have to make sure that this is the case. Then I want to talk about exploring use cases. So I'll give you a little bit of an example of current status of a couple of use cases, and pretty much give you an overview, giving you an idea about the wealth of quantum algorithms that are out there, and pretty much also the challenges we have right now. Then I'm going to go into XPRIZE, pretty much XPRIZE quantum applications, what the price is about. And pretty much we are opening a registration again for the prize, and it'll be exciting to see some of you maybe possibly join the competition. And I will explain to you why joining this kind of competition is something that you should think about if you haven't thought about it yet. Okay, so let's get going. So for example, why quantum computing? And all of us have a different reason why we are exploring quantum computing. And as you know, right now, we are kind of in this phase of development of the transistor stage in quantum computing. So as you know, the brain of all classical computers are this, even superconductors, right? Or supercomputers in that sense. Sorry, supercomputers and superconductors. Is pretty much transistor, switches on and off. So you can either have a 0 or a 1. And pretty much we've gotten really good to a point where we now can build these data centers, right? We can connect many of these GPUs and CPUs together, and we have these data centers where we can do a lot of computation. So what I want to show you here is a graph where you see on the bottom, on the x-axis, you see the years, and then on the y-axis, you can see the number called flops in terms of trillion. So flops is kind of like how many floating point operations you can carry out per second. And as you can see, this is steadily increasing, right? So right now we have, for example, NVIDIA. They have other chip manufacturers. They have brought out amazing chips. And as this grows, like the classical compute is going to increase over the years. So with this, I wanted to point out that it's not just classical computer is not just standing still. Classical computers and their capabilities is also evolving. It's always like increasing. It's still getting better and better as we speak. So in essence, quantum computing, as it comes up to speed, has to catch up to the classical compute, which is always getting better. And it's not stopping to get better. So I want you to keep this in mind. Obviously, quantum computing has these specific key concepts in quantum mechanics that we have figured out how we can use that in order to make computation possible using, for example, photons or ions or a superconductor. In case with quantum mechanics, using the ideas of quantum mechanics, we can use nature in order to do computation. So a transistor, as you know, is electrical current, right? Either you let it flow or not flow. In essence, you have a gate. But in quantum computing, you actually use nature, use a particle or an ion or an atom or a photon in order to do computation. And you have to do it very smartly. You have to think about superposition. You have to think about interference. You have to think about entanglement, and many other concepts, right? So when we get excited about quantum computing, and we think about superposition and a qubit, what gets us excited theoretically, for example, is that instead of having 10 classical bits where you have to encode 2 to the 10 possibilities, which is 1024 all at once, in quantum computing, you can do that's like you don't have to encode one at a time, right? So you don't have to do one 10-bit string at a time. You can do it all at once. So this is kind of like one of the concepts we're trying to explain, but I wanted to make sure that this is kind of like more complicated than that. You also have to think about interference, how this works together, how is entangling working. But pretty much this gets us excited. But in principle, if you have 10 perfect qubits, perfect in this case, then you can encode the 2 to the 10 possible states all at once, instead of having to do that one at a time, which you do with a classical computer. So this is a very powerful technique. And together with quantization, wave-particle duality, quantum measurement, right? That's a very interesting concept, because you have to think about how you measure. Because if you have prepare a quantum state and you do computation on it, and then you look at it, you destroy it, right? So in essence, there's also quantum tunneling. So we use tunneling ideas, or non-cloning theorem and such. So there's a lot of different theorems of quantum mechanics we're using for quantum computing that makes it very rich field, but also very complicated field, because there's a lot of things you have to take into account when you try to program a quantum computer. So I said classical compute before. I showed you this graph. It was in terms of flops, right? So which is kind of floating point operations per second. So quantum computers, if you talk to people in that kind of field that push the technology, possibly can tell you that instead of having 10 to the 18 floating point operations, right, so flops in classical computers, you could have 10 to the 23 operations per second, whatever these you want to call these operations, on a quantum computer. So that's 5 orders of magnitude more than in classical compute. And this is why everyone is getting excited, because you have this computational speed up with quantum computers if you do it the right way. And the different pictures here show you, and I know you have had exposure to this, you have superconducting quantum computer, which I show here, and then also like photonics, or you can have a trapped ion quantum computer, which you've learned about as well. So in any case, there's a lot of different technologies out there. And with this graph, I want to point out that all of these technology are at different stages. So photonics, for example, or superconducting or trapped ions are probably the more developed ones. But you can also have topological quantum computing, NV diamond, adiabatic and annealing, right? So there's spin quantum dot computing, helium atoms, you name it. There's a lot of different approaches out there. And all of these approaches have pros and cons. All of these approaches have different quality of qubits. All of these approaches have a different speed of computation. And they're all trying to figure out right now, what we're doing is kind of try to figure out what modality is going to be our transistor. If there's only one, maybe there are multiple ones. And then also having all of these different modalities, what kind of algorithm do we have to come up with? So with an algorithm, what I mean is, how do you encode the problem into instructions the quantum computer can understand and then solve the problem in? So pretty much there are many companies working on this. There are many universities working on this. There are many labs, national labs working on this. So it's a big, big effort. And it gives you just kind of like an idea regarding how much we are trying to figure out right now all at once. This is all active research that's going on right now. It's very exciting. So obviously for you, all of us who go into quantum computing, we have to understand that quantum computers will not replace classical computers. First of all, quantum computers are not very good at doing certain point of calculations. For example, addition, subtraction. That's something a classical computer is very good at, and quantum computers will not be able to replace. But on other problems, we can think about where is a classical computer eventually outperformed by a quantum computer. So what I'm showing here is one interesting plot. Here, this is a source of the paper, if you're interested. But what I'm showing here on the y-axis is kind of the time it takes to do a computation. And on the x-axis is the problem size. So how big is the problem? How many parameters do you have? How many input values do you have? And all we care about is this quantum speed up, right? So can we speed up the computation we do on a classical computer on a quantum computer? So just for scaling, this is just an example. It's not something that is, applicable to all of the problems. But just imagine here, you have a problem you can solve on a quantum computer. And when you have a small problem size, it takes almost a week, whereas on a classical computer, it takes a few minutes, right? But as you increase the problem size, you follow the blue curve, that problem scales exponentially, for example, and then eventually will blow up, right? So as you then just increase the problem size a little bit, suddenly your classical computation will take very, very long. It could take years. So what I want to tell you right now is that you can solve problems you can come up with on a classical computer. It just will take a really long time. Or you have to build a very big data center, right? So in principle, you can wait a really, really long time and solve your problem. But for practical applications, we can't wait a really, really long time. For example, if you have, if you just do some kind of like scheduling of trains, you would like to do that in real time in case a train breaks down, and you would want to have to reschedule something, right? Or if you have an airplane, it could, you are an airline, right? And one airplane falls out, or a couple ones, you have like 300 rounds, and you have to figure out how to reschedule that. So you can't wait years for that or weeks for that. You want to make that very quick calculation. But in any case, on a quantum computer, that same problem may scale linearly. So here you can see it in linear on this scale. Probably it might be a log-log scale, but in any case, in this case here, it's a line, right? The way I scaled it. But eventually what you're going to have is there's going to be a point in time where the quantum computer is going to be faster at computing that problem than a classical computer. And this is what we call quantum speed up. So depending where you are in this area, you may think about this line moving, right? So for example, people working on classical compute, which, for example, you're building a bigger data center and such, you want to shift that, that curve down, right? So you want to be faster in computation. If you work in quantum computing, if you are building hardware, you want to build better qubits. So you want to take this red, this yellow line, and you also want to shift it down. And if you are a user, you're interested in this, possibly this overlap, this cross-section, and you want to figure out how far past this cross-section do I have to be, how much more or how much faster should a quantum computer be for me to implement that solution in my company, right? For example, imagine right now I have a lot of classical compute. I have my own cluster. It costs me money to set up that cluster. I have everyone trained on using the classical computer. So when does it make sense for me to invest into this new technology? And it will all depend on this crossover point when a quantum computer suddenly becomes faster and how much it costs me to adopt that technology. So you have to understand that there's a lot of questions that are being asked in the field regarding when is this crossover and when are people actually when do people care about it to use a quantum computer instead of classical computing. So with this plot here, I want to show you something that people are very interested in. It's called resource estimation for quantum applications. So pretty much here we're interested in what modality am I using? How good are my qubits, right? Because right now we all know they have an error. And then how long does it take to compute? So don't take this again as something that is, has a lot of range here, as you can see, but it kind of like just brings the point across. It's a paper that's already 2 years old. So I'm sure things have changed in these plots, but it gives you still a good idea. So what you have here on the y-axis is your physical qubits in the millions. On the x-axis, you have runtime in seconds. And here you can see a second, a minute, hour, because we're not good, sometimes not good at translating seconds into days and weeks and such, but it shows here on the y-axis. So what I want to show you here then, and then you have this legend that says a quantum computer, right? It's all gate-based quantum computing. So it depends on how fast your operations are, right? So how fast is your operation? So if you think about superconducting quantum computer, they're very fast, right? They're superconducting. They can do operations very fast, or gates very fast. On the other hand, if you have trapped ion quantum computer, you have to physically move the ions around, or neutral atoms, right? You're physically moving atoms on your chip. So that is an operation takes more time. Then you have different areas of quantum applications, quantum dynamics, then factoring like, you factor in numbers. So that's the RSA, if you wish, and then quantum chemistry. Quantum chemistry, that's a very interesting field because nature, or the atoms, right? The way we describe them, we use the Schrödinger equation. This is inherently quantum. It's quantum mechanics. It's already encoded in the quantum language. So quantum chemistry is an area where we really think that quantum computing can help. But as you can see, for example, in quantum chemistry, depending on how fast your quantum computer can do operations, and then also with the idea of like how good are the qubits, so you're going to need error corrections. So there's an overhead of physical qubits. You can see that you need like 10 millions to 1 million physical qubits, for example, say for a superconductor, in order to start to do quantum chemistry problems that bring you to quantum advantage, right? Factoring, you need even more qubits in order to get there. But if you look at quantum chemistry right now, what we know right now from the physical status of a superconductor, for example, superconducting quantum computers, it will take you weeks to a decade, depending on where you are, in order to finish your calculation. And it will take you millions of qubits in order to do so, physical qubits, the noisy kind we have right now. So you can imagine, like, well, what kind of applications would be good for this? Maybe drug development, right? Because drug development typically goes through a long process because we have to have some test drugs. Then we have to do lab testing. We have a lot of like candidates, and then we kind of like try to filter them out. And these if you have like if you do some kind of experiments in a lab, you have animal studies, yada yada yada, right? So it takes years to develop a drug. Obviously, we had situations when we had our like epidemics that we can sometimes go faster than that, but in principle, it takes really long. It takes months to years, right, in order to develop a new drug. So if you can then possibly do a quantum calculation that takes, a quantum chemistry calculation, it takes a few weeks, and you can do a couple of different like candidates, then it might actually be good, right? But what we are all trying to do right now, we are trying with algorithms we're developing, we're trying to move these curves to a shorter time, right? So these regions more towards the left, towards the y-axis, and also towards the x-axis, so down. So as we are developing algorithms, we're trying to move this. As we develop quantum computers with better qubits, we're trying to move this. So this is just a snapshot right now, but it's very dynamic because we are making progress as we speak. So what does it mean for use cases, right? So now I gave you a little bit of an idea regarding, quantum, where we are, right? Quantum computing. I told you that classical computing is there, but don't forget that classical computing is improving as you speak. We're building these new data centers. We're building these new chips. Classical computing is not efficient, super efficient. There are things that can be improved. So I just want to let you know that classical computing is improving and quantum is still trying to catch up. Then there's going to be the cross section where suddenly quantum computing becomes more efficient. We have this quantum speed up. But if you look at the current state, we can see that we're still very far away of making an impact because our qubits are just very noisy. If that's okay right now, I would like to stop for a little bit and see if there are any questions in the audience before I move on to talking about a couple of use cases. Okay, so I'm taking this as keep going. So let's talk about the full stack of a quantum computer, and I think it's good to set the pace now regarding what I'm going to talk next. So this is a full stack quantum computer, has different layers, right? So the bottom layer, you can imagine, which is called here the quantum plane, that is where we have the actual quantum computer, right? So that's where the hardware sits, your superconducting quantum computer, your trapped ion quantum computer, your photonics device, and so on. Then you have a lot of different layers here, right? More or less like how you speak to the quantum computer, how do you translate your algorithm into language the quantum computers understands, how do you shuttle ions around, right? How do you do the pull sequence, what is more efficient, and so on. And at the top of the stack is your application. That's the problem you want to solve. For example, you have 300 airports all around the world, and you have, I don't know, 12,000 airplanes. I don't know if that's the right number, but you want to, and you have 1,000 active, for example, but you want to go around. There's a chat. Please, can you explain further the statement quantum computing is trying to catch? Yeah, so quantum computing is trying, so I got the question here that please can you explain further the statement quantum computing trying to catch up? So yes, so quantum computing right now, if you have kind of followed the quantum algorithm development, so for example, quantum computers, we come up with a calculation that we show that we can do faster than a classical computer. And then it turns out that the classical computer can do that anyways, already faster, right? Or what you're trying to do when you learn quantum algorithms, like how to implement them, you're doing things that you can test on a classical computer. So right now, when you develop a quantum algorithm, you solve the problem using a quantum algorithm, and then you check that your quantum algorithm did the right thing. And in order to check, the classical computer has to give you a solution. So in essence, right now, everything we're doing is like, we show that we can do this on a quantum computer, but a classical computer can only do that. So there's all of the applications we have thus far that are meaningful for us in everyday life. A classical computer can solve faster than a quantum computer, right? That's just the way the case is. So for kind of like quantum applications that are useful for industry, that are useful for our everyday life, we are playing catch up. And I hope that has answered that question. And then I have another question here. This week, there was a report that researchers at Shanghai University were able to factor a 22-bit RSA integer using D-Wave's quantum computer. The report is saying, okay, using annealing. Yes. So I have not read up on this report, so I can't comment on this. But yes, quantum technology is getting better. I am personally skeptical that this is possible at the moment, but I could be proven wrong. So I would have to look at that. So thank you for sharing. I have another question. Honorine, sorry if I, please.
Okay, thank you. I didn't get well what you said about quantum speed up with the graph.
So a quantum speed up, this one?
Like, no, before that. Oh, yes, here. Do you mean that quantum computers are slower than classical ones for simple tasks?
Yes. So this is not even simple tasks. It's for example, if you use right now Shor's algorithm, right?
Mm.
If you want to do factoring, you can go and you can look at factoring right now. We can factor maybe like 3 times 7, which is 21. So we can factor 21 in 3 and 7 with a quantum computer right now. But it's very inefficient. So right now, classical computer does it faster than a quantum computer. So you can think about factoring right now. But eventually, when you have a very big problem for size, when your number is becoming huge, right? And you try to factor it for RSA, eventually a quantum computer will be more efficient at it. Does that answer your question? It's not just for simple problems, it's just even for factorization, the quantum computer right now is just not as good as a classical for a small sample size. But if you have a very large sample size, the quantum computer could be better than classical computation. Did this answer your question?
Yes, I get it now. Thank you so much.
Nat?
Hello.
Hello.
Uh, so I'm trying to get out with this one. You are talking about the quantum speed up, and then from the graph, I can see that for smaller problems, the classical computers does better. So I'm asking, how about maybe accuracy? Maybe let's talk about when it comes to quantum chemistry, where we want to enhance accuracy in our calculations. Like, does the quantum computer that?
So yes, so for quantum, so there is this, what this graph doesn't show is for calculations that cannot be done classically. So quantum chemistry is a perfect example where we have to use approximations in order to calculations. For example, DFT calculations are in quantum chemistry is an approximation. We cannot even do exact calculations for quantum chemistry for big molecules right now. So we have to do approximation. But a quantum computer could in principle do an exact calculation if you have enough good qubits. And then for this problem, it would not apply. This graph would not apply. Yes, that's a good point, that it doesn't apply for all of the problems. Is that okay answer, Nat?
Thank you, thank you.
Great. For simpler tasks, classical computer is better. Complex tasks, quantum computer is better. Yes, so that's kind of like for certain calculations, it's always kind of think about what is simple and what is more complex. But typically, when you can think about something that you can't do exactly, like quantum chemistry, right? Quantum computer could be better. You could say that's a complex task if you wish. So yeah, man, you could put it in these words, but there are also very complex calculations for classical computers that quantum computers won't be able to do. For example, yeah, as you said, like addition and subtraction, right? You could do something very complex, and a quantum computer could do that if you have a very complicated way of putting your things together. There's other things where it's questionable if a quantum computer can even do that. For differential equations, for example, we don't know, is a quantum computer ever gonna be able to do that? Certain types of differential equation, are we gonna have a speed up for ordinary differential equations with a quantum computer? Likely not, right? Maybe for partial differential quantum equations or fluid dynamics, right? So it depends. So I wouldn't say that this applies to everything, that complex is better for quantum computer and simpler is better for classical computing. It depends on the problem. So I have another question. Is it because classical computers can solve these simple tasks? That's why we don't want to use quantum computers, or classical is better solving these problems. Yeah, so more or less, it's kind of like a resources, right, thing. So I don't know how much you know, but building a quantum computer right now is very expensive. Running a quantum computer right now is very expensive. You have to have a very good, very good knowledge, and you have to have a lot of people that understand a quantum computer. You have to calibrate the quantum computer, and things may get bad. If you have a photonics quantum computer, your optics can burn out. So there's a lot of stuff that can just happen right now in a quantum computer. So it's a very difficult thing to build and expensive. Your classical computer, like your laptop, is something that's around a lot. People have it. So it's easy to use, right? So obviously that's the case, that a lot of stuff right now we're using a classical computer for because it's cheap. And that's why we're using a classical.
Yeah, I heard you made a statement that yes, please. My question is, it's like I heard you say quantum computers are not coming to replace classical computers. Is that right?
Yes, yeah.
Okay, so now what I'm thinking about is now, so if quantum computers are not coming to replace classical computers, assuming we are successful in having a quantum computer, would it be a case where you have to define problems where you will need to use classical computer to solve or use quantum computer to solve?
Yes, this is exactly where we are. We are on the stage of finding these problems that a quantum computer is good to use for. Yes, so exactly that's the thing. We need to find these problems, these applications where a quantum computer can be better than a classical computer. So then we switch to a quantum computer to speed up the calculation or solve a problem that a classical computer can't solve exactly. So we're
Okay.
looking for these problems, yes.
Okay, thank you so much.
Mm-hmm.
Thank you.
You're welcome. Nat? You have your arms, you've still your, oh, okay. So maybe that's not taking off. Okay, wonderful. Okay, so we can keep going. I try to keep the chat open so I see the next. So again, I want to go through a section and then we can have questions. That works quite well, it seems. So we talked about the full stack quantum computer, and pretty much applications is where we are trying to find these problems, as Albert just said. We're trying to find these problems that we can solve on a quantum computer, and that's going to have a quantum speed up. It's going to be better than classical computer, or a problem that a classical computer can't solve, but a quantum computer could solve exactly. So then after you have this application, so your problem you want to solve, like the use case, we call it, then you have to develop the algorithm. So, and then once you have the algorithm, then it's a question of like the framework, the architecture, your control logic, your control plane, and the hardware you're using. And I want to tell you that even though you have an algorithm, so even though you can rewrite the problem you want to solve into a quantum algorithm, you have all these layers then that add complexity, add noise, add error, and add time to compute. So all of these steps you see in a stack add time for you to reach a solution. So it's very important that you understand the whole stack and you understand how long it takes for you to implement the solution, and then also how good it is. So how noisy it is, or how you can reduce this noise, or how you can make it more efficient, faster. So right now, we are lacking on these applications that we can write into quantum algorithms that are actually useful for everyone in our everyday life. So this is kind of like, so now I'm going to focus on these applications and the algorithms. I will not focus on the stack, the bottom stack, in the rest of my talk. So these are kind of potential quantum computing use cases you have seen already. You probably have kind of like explored. So you have different application areas in chemicals and petroleum, distribution and logistics, financial services, healthcare and life sciences, and manufacturing. And each of these have different use cases you can explore. For example, in manufacturing, right? We would like to, for example, work on a structural design of fluid dynamics. And that may be a machine learning and AI application in quantum computing. Or you would like to kind of like work on a supply chain. You want to optimize your supply chain, for example, for delivery or whatever. You would look into optimization. So all of these kind of like use cases are out there right now. People have started developing quantum algorithms, right? So here we started to take the classical computation, put it in a quantum algorithm, and then showed that we can reproduce what a classical computer can do. And then we try to estimate what kind of quantum computer would I need in order to outperform the current classical state-of-the-art application and solution. So this gives you an idea. Obviously, there's a lot of new use cases we are exploring, but that kind of like just example of what you can see. Obviously, chemicals, a lot about catalysts and surfactants, right? If you can catalyze a chemical reaction, you can speed it up, right? You can make it more efficient. Surfactants, for example, you can code something in order for something to be better drug, so being like better taking up, for example. So there's a lot of different applications. But I won't go into all of them, but just gives you an idea. So now what about quantum algorithms? So quantum algorithms, you can think of different layers there as well. So first of all, I want to outline here that you have different layers in this graph. So the top layer is your problem, the problem you want to solve. For example, you want to solve a partial differential equation, Navier-Stokes equation. That's your fluid dynamic problem, right? So for example, you want to figure out some fluids, plasma, for example, fluids, water, or you want to make something more efficient in your turbulent flow, you name it, that could be Navier-Stokes equation, right? If you want to study combustion, right? You want to build a better engine. You want to take a rocket, right? You want to explore space and you build a better engine. You want to make sure you come back or something. That's all like Navier-Stokes fluid dynamics, right? It's combustion. These are waves and we're trying to model. Machine learning, for example, is one problem. So there's this idea of how can quantum computers be applied to machine learning. For example, if you take a chemistry problem, right? If you want to do some analysis on the best chemical for a certain application, what you could do is you could use a quantum computer to calculate an exact structure, chemical, like like different energy levels for different chemicals. And you could figure out, can have like many different chemicals, and then you could use machine learning in order to learn from that data and develop something new out of it. So then once you have the application, the second layer is your algorithm. So different algorithms you have probably heard about. For example, Grover's-based algorithms, search algorithms, phase estimation, QAOA, factoring, right? QUBO, Ising model, that's kind of like the D-wave approach where you have, your energy landscape and you try to fall into the minimum. So there's a lot of different algorithms you can explore. And then you have different quantum toolboxes. So this is kind of like how you build these algorithms and how do you apply them. So in essence, you have to think about these different toolboxes, which is on the bottom. And then you develop algorithms from these toolboxes, and then you are applying them to a problem. Then you also have the color code. You have the NISQ devices. So this is the noisy intermediate state quantum. The noisy quantum computers we have right now. You have the QFT, so quantum Fourier transform based. That is thought to bring you quantum advantage. So if something is quantum Fourier transform based, because it's a way of speed up. Light blue is gate based quantum computing, and then you have analog quantum computing. That would be, for example, D-Wave, right? Annealing quantum computers. But what I want to show you here is that you kind of have to use these different toolboxes in order to build your quantum algorithm, in order to apply it to a problem. But not all of the toolboxes can be applied to all quantum algorithms. And then also not all of your quantum computer modalities can solve specific problems, right? So it's said that gate-based quantum computers are universal quantum computers, and they can solve any problem. For example, a annealing quantum computer can solve. Can it solve any problem as fast as a potential annealing quantum computer? We don't know. But in principle, you can solve it. But how fast is this quantum computer is another question. So one thing I want to maybe also emphasize here is that what that graph doesn't show is that when you do quantum algorithm development, the majority of the algorithm is still classical. And then you have some parts of this classical algorithm which you can replace by a quantum analog. And then that gives you that speed up. So I want to say here too that even if you develop a quantum algorithm, there's still a lot of classical pieces in an algorithm that you need to use, right? So maybe you have coded something up, a quantum algorithm, and there's still for loops, there's still if, there's still a lot of classical algorithm development within a quantum algorithm. And I want to emphasize that too, that you really have to understand these toolboxes. So different ways of speeding up classical computation when you develop these algorithms. So then you can talk about speed up. So this is again a snapshot. It doesn't have to be this way, but there are things that we are working on right now. So what I want to show here is it's a fairly busy plot, but pretty much what you have here again is you have different algorithms, quantum algorithms like VQE, QUBO, QAOA, variational quantum machine learning variants. So you have different layers here, search algorithms, machine learning, and other, and then you have the speed up. So what we talk about here, this is the speed up which the plot I showed you, right? So you want to have quadratic speed up, or polynomial speed up, super polynomial speed up, and this kind of shows you where you are. I have another question in the chat. Let's see. Yeah, so Monte Carlo simulations is also one. So there's a quantum there's Monte Carlo simulations. Sorry, I have to go back. There's Monte Carlo simulations, and then there's a quantum Monte Carlo simulation. What we believe right now, this quantum Monte Carlo simulation has a quadratic speed up. So it would be here. So right now, it's not 100% sure that quadratic speed up will be enough for a quantum computer to outperform classical computing, because you have so much more, because you have to still do the operations, and there's still this time a quantum computer has to spend. So it's unclear if theoretical quadratic speedup is going to be enough in order to outperform a classical computer, because they're so well developed already. So what we believe actually right now, if you talk to quantum algorithm developers, they will tell you that you kind of need exponential, so super polynomial speedup is kind of where you have to be in order to kind of have this quantum advantage that we would like to explore further. And if you look here, anything that is super polynomial speed up, you really have to have fault-tolerant quantum computing. So that means that we have a lot of physical qubits that we are able to encode, such that we have a logical qubit that has an error rate of 10 to the negative 8, for example. And that's kind of like fault-tolerant quantum computing, where we feel like that quantum computers can actually have this quantum advantage. It's very specific algorithms right now that are applied in this area. And for each of these algorithms, we kind of have an idea of how many physical qubits would we take, how many logical qubits would it take, how long would the computation take. So we're trying to estimate all this right now in order to figure out where this crossover point is in our graph. I do want to point out, which is something very interesting, is that when you study quantum computing, you will learn a lot about VQEs and QUBO and QAOA. And actually, it's kind of like unknown speedups still. Like there is still this question about, are we going to have speedups with these kind of algorithms? And we're still trying to develop these algorithms, but it's unclear at the moment. So anyways, limited quantum advantage, which we think quadratic is the case. We'll see where it goes from there. So for VQE, is it not quite basic to use classical algorithms? Yes. So at the moment for VQE, we're using definitely classical algorithms to do this computation. There's also something called a quantum. So there's possibilities of using like VQEs that with machine learning in combination, and then kind of like using a quantum algorithm eventually to speed it up. But it's not proven at the moment that we're gonna have significant speed up with VQEs. So yeah, so at the moment, so if you have implemented a VQE in a quantum computer, you know that it takes a lot of like shots. You have to do many times because you have to find this ground state energy, for example, right? It takes a really long, many shots, many runs of your algorithm in order to arrive it, because it's a hybrid loop. So you're using classical optimization together with a quantum algorithm in VQE. So it's very time consuming right now, not very efficient. So now I want to talk about kind of like a couple of applications here. So molecular and material simulation. So right now, again, we are pretty good at using quantum computers to do small molecules. They're not as efficient as classical computers, but we can do small molecules right now, and we can show that we can get very close to the classical solution. So eventually, what we're doing right now for more complex molecules, which I show here on the right-hand side of the plot, for example, a protein structure or this FEMO cofactor, which is very important for certain applications. Right now, when we have these more complex molecules, what we're trying to do is try to do a resource estimation. So we try to figure out from what we know, from the molecules we can solve exactly, and from what we know, how many resources we need, and from what we know, what kind of quantum algorithms we can apply to solve the chemical structure for these molecules exactly with a quantum computer right now. So from what we know, how to do this, the simple examples, right, the smallest molecules, how can we now estimate the resources on a quantum computer we would need in order to do more complex molecules? So that's what we're doing right now. Then all of these right now is hybrid quantum classical algorithms, right? So you have part of the computations are done on a classical computer, the classical algorithm, and then you send some calculations off to a quantum computer. Right now, especially kind of like what we are doing a lot is error mitigation. So we're trying to figure out the error. How does the error scale? How does the error behave? And by understanding how the error behaves for small samples, for example, we could then extrapolate that error, how it's going to behave for large samples. If we have a functional dependence on the error, we can then correct for it, but you have to oversample, which is a problem. Quantum error correction is one thing we do a lot in quantum chemistry. Is trying to figure out how can we use quantum error correction for these specific algorithms. And there's more going on right now. But this is kind of what we do in molecular simulations right now. We know small molecules, how to do it, how it works. We've shown that it works. And then we're trying to estimate what resources we would need in order to do more complex molecules to get ready once we have better quantum computers. So here, I want just to show you a sample history. So this is kind of like this asymptotic scaling of quantum algorithms for quantum chemistry simulations. So here, what I want to show you is kind of like how did the quantum algorithm development go over the couple of years. So what you see in the leftmost column is the year. So in this specific image, you can go to the PRX here in order to look at that. You can see how like who worked on this problem over a couple of years. So I do have a question. So Nat?
Please, I want you to clarify the quantum error mitigation and the quantum error correction. So right now, I understand that both of them are to counter, maybe to ensure we are close to the right value as possible, right? And then, so like, which one of them is actually better, and which one has got many applications right now?
I would say a quantum. So all of them are still under development, I would say. Quantum error mitigation, I believe, if I'm not mistaken, is highly applicable for the noisy qubits we have right now, because we are producing error, right? So the noisy qubits produce error, and as we add more qubits, we produce more error. And if we understand the functional form of this error, we can correct for that error as we increase the qubits, right? But we have to have some error, underlying error. So for error mitigation, you have to have this underlying error, and by understanding how this error scales or how this error behaves, you're trying to correct for it. There's a lot of errors. So I told you about the quantum stack, right? So there's a lot of different errors. You could have errors in applying the gates, right? So you can apply more gates, figure out if you apply more of this to full, like 2 qubit gates, how does the error scale, and you try to correct it, right? But you can think also there's an error in the way you are controlling pulses in a quantum computer. For example, a certain pulse sequence always gives you a certain error, a different pulse sequence gives you a different error, and then you try to correct it, right, in terms of like pulses. The pulse may not look smooth, right? So maybe your pulse is noisy. It has a couple of spikes. Instead of having a smooth Gaussian, you maybe have a contrived Gaussian. It's kind of shifted to one or the other side, right? But if you can correct for that shape in your pulse, in your electronics, right, you can do this error mitigation in electronics, for example. So error mitigation is not just working on your qubits, on your gate level. It could be anywhere in the stack when you control the way you like kind of take the algorithm, rewrite it into like a language your quantum computer understands. There's a lot of ways where errors can add up and where you can mitigate errors. For example, another example would be electron levels, right? If you have lasers, in order to promote electrons in different energy states, you may fall into a triplet state, a different state you don't want to be in. Sometimes you can, some things you can't control because it's just fundamentally physical, but some others you may be able to control because you could control your laser line to make it more narrow, and then you could be better mitigating that error. So there's a lot of wealth in error mitigation. I don't think we fully understand it. Quantum error correction is different. Quantum error correction is really thinking about how can I like have multiple qubits come together to make a logical qubit. Okay, so it's a different way of things. So quantum error correction is also still being developed, but in essence, quantum error correction is different than error mitigation because quantum error correction works on actually the physical qubits, how you build logical qubits. Whereas error mitigation, you try to figure out how the errors in your system behave and you try to correct for them. Does this help?
Yes, thank you, that was very
good. Thanks. Good questions here. So now going back to this plot here, we have the number of years. And then in the first column, and that's just like there's a lot of different stuff here to look at. But this is for a specific, scaling quantum algorithms for simulating quantum chemistry in an arbitrary basis. So some kind of like molecular orbital you want to simulate. Obviously, you look at try to estimate the Hamiltonian eigenvalues using phase estimation. So it's a little bit specific. You can read through the figure, the table caption if you wish. But all I want to show you is that in the middle, you have different innovations, right? So you have a quantum algorithm that calculates this, estimates these Hamiltonian eigenvalues, right? And then you realize this quantum algorithm can be improved by doing something, right? For example, I can use a tighter Trotter systems for doing the Trotter bounds. So if you go through Trotterization in time series, you could make something play with the bounds and you could do a better job. Or you can randomize things, you can start factoring things. You could have, you can use tensor, hypercontraction, for example, which is this work, specific paper. And all of these different technique in an algorithm trying to figure something out to make it better. If you look at the complexity in Toffoli or T-gates, right? You can see that the order of how many gates you need in order to do that has been always decreasing. So this order, so polynomial, right, in n compares to the order of n, right? This is like a big increase, or to say decrease in complexity. So these algorithms get less and less complex, and you need less and less gates in order to develop that algorithm or apply this algorithm, right? And then obviously, you think about different complexity, the space complexity and the T complexity, but in any case, it just shows you how algorithm develops, right? So here, this is, for example, n to the 10, and then we went down to n to the 4, n to the 2, right? And then here it's just dependent on n, right? No dependence, no like factor, right? So in S case, you can see how it becomes easier, simpler and simpler and simpler. And this is 15 years of development for a specific application. So as we speak, we are getting better and better, making these algorithms more efficient. But this is a long process, right? It takes time. So another one is for partial differential equations. So again, you can think about how has this been developed over the years. So here we kind of like look at the time complexity solving d-dimensional partial differential equations. So partial differential equations are very difficult to solve. When you learn about PDEs in mathematics, right, you kind of like learn the ones you can solve exactly, but eventually you can't solve these exactly anymore. You try to use a classical computer, right, a computer to solve them for you, using numerical simulations, for example. And then at one point you're going to have to do, even there, you have to do estimations in order to solve a problem or kind of get a close answer to something. But again, what I want to show here is that these complexities, if you look, also change over time, right? So you can have different types of complexities for the PDEs, and depending on classical method or a quantum method, you have different equations you can think of. Poisson equation is very specific, or the wave equation is very specific, right? Or a general equation is what you would like to have. So you can see exactly here that classical has a more general application compared to quantum algorithms. Boundary conditions, again, classical is way better because you can have any general boundary conditions, whereas quantum algorithms have to have specific boundary conditions where they can be applied, right? But then if you look here, you have all kind of this polynomial complexities, but here you could see that quantum, you could eventually could kind of like to the d-dimensional PDs that seem to have a little bit better scaling in terms of complexities. But on the other hand, they're not very general yet, right? So they're very specific applications for quantum compared to classical. So I just want to tell you that there is a lot of work being done here, but you can see that quantum is not as general as classical, but where quantum can be applied, very specific equation for very specific boundary conditions, you could have a better performance in terms of the complexity. Then another example I want to give you is this quantum algorithms for fluid dynamics. So this is an example. Again, there's a paper, recent publication you can look up. But that kind of like shows you where we try to estimate the resources. So there's a lot of, on that flow chart here, there's a lot of classical compute. So you have classical workflow, you're doing encoding input on classical matrices, you're doing block encoding, it's all classical here. And then you eventually have a quantum piece of the calculation on this hybrid calculations wish, where you then do quantum amplitude amplification and quantum amplitude estimation. So then in this workflow for fluid dynamics, eventually you have some quantum algorithm that gets inserted into this classical workflow. So this is very kind of like where the state of the art is right now. It's a lot of Hamiltonian encodings. So you try to figure out what kind of Hamiltonian you apply here to solve the system. But this is really something that these estimates here would be like 10 to the 22 to 10 to the 28 logical qubit gates times the T gates in your algorithm. So these are kind of scales that a quantum computer would take very, very long time for us to get there. We're not even there yet to have logical qubits, right? So the logical qubits we have right now are just a little bit better than your physical qubits, maybe by an order of magnitude, maybe by 2 orders of magnitude, right? But in order to really, that would be 10 to the negative 3, 10 to the negative 4, 10 to the negative 5. So out of like 10,000 times you make an error, right? So that's where we are right now with our, fault error corrected quantum computers. But logical qubits are, 10 to the negative 12, for example. So we're really far away from having this kind of quality qubits. And then you need 10 to the 22 of these kind of logical qubits. So we really need to do more work in this quantum algorithms for fluid dynamics in order to see kind of an advantage that's reachable for us for a quantum computer. Okay, so now I gave you hopefully a good idea about like where kind of like things are right now, what you should be thinking about when you think about where is a quantum computer useful or not, and then kind of understand that for each of these applications, we try to figure out what quantum algorithm we can use. A quantum algorithm is very much based on a classical algorithm where you have small parts of them, and a classical algorithm where you try to find the quantum speedup. And we still have a lot of work to do in this field. But there's progress being made, as you have seen in this table I showed you, where the complexity has been decreased for quantum algorithms over a decade for certain examples. Okay, so I'm happy to take some more questions, and if you're good, we can keep going. And I got a question. Please, how will having a theory of everything get us closer to full implementation of a quantum computing? So what do you mean with a theory of everything?
Okay, so this is where we get to understand all the theories of quantum physics and how it relates to all the other fundamental forces.
Oh, okay. Oh, I'm probably not the right person to delve into this topic. Unfortunately, I will not be able to like dive into this because I haven't really thought about the theory of everything and how it can get us closer to implementing of quantum computing. But my guess here is that, if you understand certain, so there's this idea that we still don't fully understand all of the quantum mechanics out there. So if we get to that theory of understanding quantum mechanics fully, we maybe have overlooked something when we develop quantum computers that could make it more efficient, right? So that's the only thing I can tell you. By finding new theories that we haven't seen yet, and then they may have an impact, then possibly there should be changes in quantum computing. So can't really go further than that, unfortunately. Quantum inspired algorithms, yes. So there's this idea of using algorithms that are quantum inspired. I think it has been very successful to do quantum inspired algorithms for classical computations. I'm again not an expert for that, so maybe you can ask a speaker who actually has experience in quantum inspired algorithms. Yeah, so quantum inspired classical, exactly. So there's this work which is people are doing where you can use the quantum language and then, you know, apply it in quantum and classical algorithms. When probabilities, for example, is something where you can imagine quantum mechanics is probabilistic. And then if you have a classical algorithm that works with probabilities, you could, for example, imagine that by rewriting a classical algorithm in using quantum mechanical language or quantum mechanical mathematics, right, that you could have a speed up for a certain classical algorithm. But again, I'm not the right person to ask that question, unfortunately. They're successful. There are definitely some examples you can see where it has been successful. Yeah.
Oh, please, I have a question.
Mm-hmm.
So I don't know. I was wondering, has anybody done, like, maybe did some work on how quantum teleportation can help us in maybe improving our space exploration, maybe be able to capture more information out there?
So capture more information. Can you clarify that?
I mean, taking quantum teleportation, for instance, our ability to actually it's like our ability to enhance our distant communication, like
Oh, yes. So now I know what he's saying. So yeah, there's a lot of research in this area, I think, for teleportation and how it can improve our communications over you know, fast distances. People are using even our current you know, fiber optics, fiber cables we have dug in, right, and connected different labs, and people are working on that. So how can you teleport information very effectively? So yeah, there's definitely work out there. But again, you know, this is something that an expert should probably tell you more about, who is working in this area, can tell you kind of like what the status of that field is.
thank you.
Mm-hmm.
Hello.
Yes.
Hello. Please, may I know the difference between quantum teleportation and entanglement, quantum entanglement? Are they the same or they are different?
Can you repeat, please?
I want to know the differences between quantum teleportation and entanglement, quantum entanglement, teleportation and entanglement, quantum entanglement.
Oh, quantum entanglement and quantum teleportation.
Yes.
I think as is with many of these quantum concepts, quantum teleportation, you know, has like, when you like develop that kind of concepts, you have to like take all of the quantum mechanical concepts into like account. So if you want to teleport information right now, my understanding is that you have to have some form of kind of like, you have to like connect the two particles somehow, for example, to have kind of like like information sharing, right? So in essence, you can think about entanglement as one form of doing that, where you entangle the two photons, right? For example, or whatever you want to use in order to then share information. This is what we're doing right now, in essence, because that's something we can do in a lab, right? We can create entangled photons, and then we can send them to different locations, right? And then we can do a measurement. It really depends on kind of like what we can do in a lab and how we can test theories, right? I can't I would not be in the position here to understand quantum mechanics fully in order to tell you, like, if there's something in teleportation that's, would say that it is not based on entanglement. That would be my first kind of like idea here. But really, it's something based on right now. We are able to do something in a lab. We are testing something in a lab. We can entangle photons, for example, and then we can do tests on them. So right now, by like having information being transferred that way and then measured and then tested, we are using entanglement for a lot of these applications. So let's get going here. So now I would like to talk about XPRIZE quantum applications. So this is the prize I am very much involved in on a day-to-day basis right now. And first of all, XPRIZE is a foundation, and it is 30 years old, and it's kind of inspires humanity to achieve something, right? Anything that is accelerating our being, right, in order to have an equitable and abundant future for all. So kind of like solve problems that helps humanity to have a better, place on Earth, and that things are going better than they are right now. So it's all based on kind of the concept that if you have a competition, then we are kind of getting the best out of us. And it started with kind of the idea when you had the Rotate Prize, where you kind of like launched commercial aviation, where you went across the ocean, and you were able to do that. So Charles Lindbergh was able to do that, and he received a prize for that in 1927. So XPRIZE pretty much started with the Ansari Prize, where pretty much we were trying to figure out, can we have a commercial spacecraft going up and coming back, right? So pretty much we wanted to make sure that in 2000, for example, space travel was, governments were only able to do that, and it was not commercial. So not everyone was able to do that. So in essence, for us, in order to leave Earth eventually, we have to have some way of making this more available to us. So like XPRIZE was kind of like there with the Ansari Prize, which was a $10 million prize in 2004 to galvanize kind of like the area of commercial space travel. And Virgin Galactic came out of this XPRIZE, the IP. So it was kind of like very important for us to run this. So I don't have to. So we have these grand challenges right now in our areas, and pretty much XPRIZE is trying to push the limits in different areas, and one of them is deep tech and quantum. So what I want to say here is that XPRIZE has launched 30 prizes over 30 years in these different areas, and we have many scientific publications. Out of these, our teams have developed, and we have a lot of trademarks and IP. But pretty much what XPRIZE does, it pushes the technology. And the specific XPRIZE for quantum applications, what that is all about is that we were trying to find an area where in quantum computing an XPRIZE could make an impact. And pretty much we have found out that quantum algorithms are not very advanced right now, and quantum computers will take more time in order to be developed fully. And then currently they're lacked on real-world applications. Commercial or interest, could be better, more or less. It's kind of like a talent pool that is lacking. We don't have enough people in quantum algorithm development. Also, it's very concentrated. You have the quantum technology and the quantum computers being built and developed at very specific places, right? It's not very well and not very diverse. So, and quantum, there's a risk on this, there's this risk of hype, right? So that quantum computing is overpromised. I showed you kind of like all of this information. We're on quantum algorithm, where we are, what we need to do in order to solve problems. And there's this hype that's happening right now where we overpromise and quantum cannot deliver, which is a problem because then we don't have enough funding. And then governments need to kind of establish regulations and standards in order to have responsible use. So XPRIZE, even though with 30 prizes over 30 years, together with the sponsors of Google Quantum AI and Gesta, pretty much decided that we need to have a prize that pushes quantum algorithm development, because we're not having the algorithms in order to solve problems that are impactful for humanity. So if you think about the grand challenges, right, you can think about the sustainability goals, if you wish. And these sustainability goals, like the United Nations have developed. For example, you know, we want to have clean water for everyone. We want to have healthcare, or like, you know, drugs, for example, for everyone to use and such. So, however, despite this investment of the UN goals, we pretty much are not on track, right? So we are needing technology that brings us to on track. So is quantum computing okay? So let's go back to XPRIZE. So XPRIZE quantum applications. So I told you that pretty much right now at this point in time, we are lacking on quantum algorithms that have applications that are outperforming classical computing. So we don't have quantum advantage for quantum algorithms right now that are useful for us in everyday life. So pretty much we have this XPRIZE, which is called XPRIZE Quantum Applications. It's a $5 million competition supported by our title sponsor, Google Quantum AI, and presenting partner, Gesta. So Geneva Science and Diplomacy Anticipators. And it's a 3-year competition. It's a global competition, so anyone can join. And what you want to do is develop quantum algorithms, then can put into practice to solve problems that are real-world challenges today. So pretty much here I want to show you the board, so you may recognize some of our board members. So pretty much our board is made out of experts that are trying to help us design this prize. Help us design kind of like how do we judge this kind of competition when we develop these algorithms. So teams develop these algorithms for real applications. And then we also have many professionals that joined us for judges. So you can see here the experts that are part of this prize and are trying to help judge the prize in order for us to find these algorithms that have real-world impact. So pretty much what I want to give you here is an overview of the competition. So what is this competition about? So pretty much the competition wants to push 3 types of contributions, which is develop a novel algorithm for solving a new class of problems with quantum advantage. So quantum advantage, I guess, where you have a computation that is better than current classical approach. Then you also can have a new application. For example, you have a quantum algorithm that was developed for a certain application, but you realize that you can apply it to a different application and you're going to have quantum advantage. Or you can enhance the performance of an algorithm. So I showed you in one of the plots where over time it just begun better and better, right? You decrease the complexity of your algorithm. So you can also decrease the resources required to make an algorithm more near term. Again, you have to have quantum advantage, and it has to be applied to a real-world problem. So what would be these impactful applications? For example, you can think about the UN sustainability goals, right? Zero hunger, for example. Can you develop kind of like a way of fixating nitrogen, right? In order to help food production. You can maybe, for good health and well-being, you can improve the speed of drug development, or for climate action, we can create materials that capture, for example, carbon. So all of these are big problems humanity faces. All of these computations are very expensive on a classical computer, and a classical computer is in its limits, right? So can we have a quantum algorithm that can solve one of these problems in a way that it actually is feasible to solve within 2 weeks instead of, for example, taking years on a classical computer? So judges will pretty much be looking at the following. If you have a quantum algorithm that has a quantum speedup, right? And it's applied to a certain application, for example, developing a new drug that is very useful for humanity. Judges would look at the magnitude of this real-world impact, estimate the resources requirement for quantum advantage. For example, how many T-gates do you need? What would be the runtime? So how near-term is this application? What kind of fault tolerant? So how many logical qubits would you need? Then how strong is the evidence you're giving? And then kind of novelty. So how big is the thought delta introduced in your solution? So in the guidelines, if you look at the competition, you have different ways of doing this. You can have a novel algorithm. There is an example for the speedup, quantum speedup for tensor principal component analysis. So this is it's a great quantum algorithm. It has quantum advantage, but it doesn't really have a real application. So you would have to figure out what is the real world application for this, and how do you estimate the resources needed for this quantum advantage. If you have a new application, for example, solving Hamiltonian, so it solves kind of linear equation solver. So using quantum linear systems to solve Hamiltonian simulations for a superquadratic speedup. If you want to do, for example, simulate classical waves, right? That has a broad applicability. There's a quantum advantage. But again, what are the resources you need for this application? What is the real world application for that? Then enhanced performance. For example, you want to have the FEMOCO nitrogen fixation is a catalyst. Again, there is an algorithm that shows a quantum advantage, right? But maybe it needs to be more, the algorithm maybe needs to be more novel. It has to have like something that is somewhere in the algorithm you're trying to enhance, right? Make something better. Maybe the idea has to be more novel. And then again, you have to kind of do the resource estimation. So again, this is kind of an example, and these are papers you could look at, and then you can figure out what is needed in order to probably improve it and then apply it in order to be competitive in this XPRIZE. So for those of you who are interested in joining the competition, we did have a first registration window, which was in March 4th to July 31st. But we're now opening a second registration window in November to December for a month. And pretty much for the first year, which is phase 1, which goes up to August 2025, is where we're going to have up to 20 teams that will split $1 million. And then in phase 2, which is then starting more or less in December 2025, going on till March 2027, when we announce the winners, we're going to have $3 million for the winners. Up to 3 winners will split $3 million, and then we're going to have some runner-ups. So this is just the prize purse and the opportunity for you to still join the competition. And this is kind of like currently overview. And this is kind of obviously also want to point out why I'm thankful for being able to speak to you today, is that right now we have 240 teams registered. Out of the 240 teams, we have about 20% that do SDG related topics. But if you look at the contribution from, for example, from Africa, you can see that we only have currently one team that is in the competition. And I would really like to have more of your ecosystem join, the African ecosystem join the competition. I think it would be wonderful to have more teams join the competition, because we really need to have ideas and input from different people in order to solve these very difficult problems. And if you're interested in joining, and I have a question here. Yes, I will share a link with you to explore the competition. So I'm gonna do what I'm gonna do right now. Let me stop sharing and let me get the link in there. I'm just copying the link into the chat if I can. So yes, so one African country, and I just put the link in the chat for the XPRIZE. So please go it. So it's XPRIZE Foundation. Thank you. Okay, I'm gonna go back and share the slide. Okay, so I can tell you a little bit more about the competition. So if you go to that link I sent you, there's then also the guidelines. So it's a document that you can read over the guidelines of this competition, summarizes the high-level guidelines and how you apply for this competition. The competition is conducted in English, and there's a couple of registration steps. The guidelines are not fully developed in terms of judging criteria, so they're going to be more information we will share with the teams. But pretty much the guidelines kind of give you an idea about what the competition is about. And pretty much we should join the competitions because you can drive the impact of quantum algorithm development, and you can really get connected to kind of this ecosystem. So you can kind of advance the field by being part of this competition. There's a big thing about collaboration. So we want teams to collaborate with each other and kind of join the XPRIZE network, because we have 30 prizes over 30 years. We have 30,000 people that joined the prizes. And it's a very great network to be part of for your future, career opportunities, for example. And the teams can be very diverse, right? So you could be in quantum information science. You can know about classical computation. You can know about domain expertise. You could be a good engineer and know about the technical implementation. And you should possibly can know more about the impact assessment, the social good assessment of the need of a solution. So we really need a mix of people to join this competition in order to kind of drive it forward. So we're looking for enthusiasts, people that are driven by solving something very difficult. It could be students, it could be people from different fields. I really want to have this collaborative problem solving that will help push quantum algorithms forward. And XPRIZE will support teams throughout the competition. There's going to be access to experts, so you can ask questions in terms of how certain things are interpreted, right? So how a rule is interpreted. Different phases in phase 2, for example, there's going to be experts that will help you possibly understanding how you do estimation of your resources, how do you quantify social good, for example. And then obviously there's going to be this translational impact we can help with, once you have a solution, what is the impact of your solution and how do you bring it to the people so it can be used. We also have, for registered teams, we have a Slack channel where people can change out ideas and collaborate. For this, teams have to be registered. And you can share resources and start collaborating. So team registration, I did send you the overview link. So this is where the registration is going to open. I can make sure that you get the information once the registration opens. You can join as an individual, or you can participate with multiple team members. You will own the IP. This is all yours. this is your technology. It's independent of the competition. It's your technology, your methods, and your intellectual property. Open to any persons or entity, bearing restrictions by U.S. law. So you can join the competition. But there's this registration fee of $50, but for teams that want to join and have difficulties for this fee, you please reach out to me, for example, and there's a way for us to waive that fee if need be. Okay, so this should not be a barrier for you to join a competition. It is really something that we can waive for people that can't afford the registration fee. And then please you just let us know and we will work with you. So don't feel this is a barrier. The same thing with like forming a team, having an entity as a team. It's something again we can guide you through. So please reach out to us. So these things of the registration process should not be a barrier. We're here to help you and guide you through these steps. So I think we don't have to go this. But pretty much the registration process. There's one question. Yeah, I hope you can. I hope you really reach out and kind of ask questions through the process. And again, I will let you know when the registration opens. So pretty much you create this like Bob account. You complete the registration when it's open. It's a registration form. It should take 5 minutes. To 10 minutes, then the registration fee, but you can reach out to me or to this email here, qc@xprize.org. You can reach out and then we can waive these fees, the registration fee for you. And then there's this competitor agreement that is a document that needs to be signed. But again, we can help you understand these steps, and we can definitely help you get through these different registration steps. So again, I want to emphasize here that how you can get involved. So registration will reopen November 11th until December 13th. You can go directly to the website to read up on it, or you can email us at qc@xprize.org. And I guess that being said, I think this is it what I have prepared. And we can definitely now take questions if there are more. So maybe take a screenshot of this here. Criteria to join. So pretty much anyone can join. It is open to anyone. You don't have to be an expert in quantum computing. Anyone can join this competition. So really the criteria to join is like once we open the registration back up, there's going to be a registration form that asks you about the background, why you're interested, what would you like to do. You don't have to have a solution yet. You can say, I'm still working on it. And then once you can complete the registration form, you reach out to us to get the fee waiver. You get a code which you can use in order to waive the registration fee. And then you sign the competitor agreement. It's all done online, and we can walk you through this. Is the competition focused on quantum applications alone? The competition is focused on, yes. So you have the competition is focused on quantum algorithm development. So it's an algorithm development for a specific application of the algorithm, right? So then what kind of application could that be? Something that impacts humanity, right? It could be differential equation because it is used in many computations. It could be something in quantum chemistry. So it's really widely applicable in that sense. It could be an image analysis, right? Because image analysis is something we need in order to, for example, develop new technology in order to look at the biodiversity of, the rainforest, for example. So there's a lot of applications you could do. We have your own contacts. Yes, so I can do that right now. I'm gonna put in my email. So Kathrin's email. So if you want to email me, which I just put in there now, so Kathrin.Spandier@xprize.org. Please email me directly, and I can then connect you to our Teams relation manager and myself, and we can walk you through the process. So I'm still trying to. So maybe I can turn on my video again. So it's a little bit bad. Yeah. So here's my video again. I can turn it on, I think. Okay, so other advantages. So even if you fail the competition, so really, we have now tried to develop a network. So by joining the prize, even if you don't make it through the competition, we really want to connect you to the ecosystem. So what you have seen is 240 teams all over the world, right? These are students possibly starting their quantum journey. These are people that are possibly very interested in learning from you, from your expertise, where you're coming from, why you're joining, right? So it's really about networking. So even if you don't move forward, right, you can really network and make connections with people, figure out what they're working on. And then I would say that there's another thing of like, you can join teams. So if you have, for example, an idea, or you have understanding of a quantum problem, right, or like an application you would like to do, or you have an experience in a certain part of the competition or like application, then teams can join. For example, you can join teams that are looking for members, that look for increasing the team count to work on different problems in their solution, right? So teams can merge. So, for example, even if you don't make it through the first phase, you could merge with other teams to make your team stronger, and you can re-enter the competition in terms of a wild card. So there are many ways of trying to give you something back. And then you have the networking I want to talk to you about, and then our Jesta. So we're working very closely with the Open Quantum Institute. So that is another thing of like, as you come in, you grow a team, and then you're joining forces, right? You become, you network, become an entity. And then obviously there are some things that we can follow up, and then we can also work with the Open Quantum Institute, for example, in order to help you for further steps in your interest in quantum computing. So it doesn't just end with XPRIZE. How many are required to form a team? You can form a team as an individual, like one person can join the team, and then you can add people to your team if you want. Or you can only have 4 or 5 people, or you can have 20 people, or you can have 50 people. There's no limit on the numbers. You need at least one person to form a team, and that's the requirement there. Can individual representing governments make propositions on behalf of countries, like funding opportunities to help improve the economy, create jobs, and contribute to the 17 UN Sustainable Development Goals? So that so Dr. Peter, I think I have to think about this question a bit. Then concerning the team, do we form the team before registration, or we register as individuals first? You can form the team during registration or before registration, or you can join as individual. So you pretty much can, the team can change over time. So it doesn't have to be, you can add team members anytime during the competition, pretty much. What are required for team formation? So for team formation, all that's required is that if it's individual, you are signing up once the registration opens November 11th. So please reach out to me directly so I can make sure that you are informed. I also will share the information with Dr. Henry. So he has it when it's opening. And then pretty much you go through the registration steps. So once you start the registration process, we can look at your registration process, and then we can walk you through the different steps, for example, via email, to make sure that you are doing all the steps in the registration process. Dr. Peter, are you online?
Yes, I'm online.
Can you explain your question to me?
Okay, I just wanted to find out, as I'm an academician, at the same time, I'm also part of a government into politics. So, if you want to come up with a project, a national project that can actually help Ghana in terms of quantum computing, developing innovative applications and projects to help advance the economy, create jobs, and also contribute to the 17 UN Sustainable Development Goals. I was asking if it's possible that those individuals can actually come and seek for funding in order to realize something that they want to do in that line.
Oh, okay. So XPRIZE, so the way the competition is structured is that the prize purse is given after different milestones have been achieved, right? So teams have to, in terms of funding for the competition, teams have to find their own ways of working on the competition. That makes any sense? So XPRIZE is not is different from a grant, right? Where you propose something and you work on it. XPRIZE is giving the prize purse after a competition has during a competition after the teams have achieved some milestone. So if you work for the government and you have funding through a government to do a project, right? And your team and the government you're working with, you have an agreement on the solution. And the agreement is that you own the IP, right? And there's some kind of a relationship between the government and the team, for example. Then you can join obviously the competition as long as everything is okay. So we don't have any kind of requirement on like the funding you're using for your solution. As long as you own the intellectual property you're developing, right? And as long as you have an agreement with your partner that it's okay for you to join the competition. Does this answer your question?
Okay, so if I get you clearly, it means that there is more of a competition. There is not a place for you to seek for funds, but to also partake in a competition, a worldwide competition that is ongoing, so that based on your ideas and your assessment and all of that, maybe you can be given help financially to continue with your project.
Right. Yes. So that's what I want to say for example, Open Quantum Institute, for example, right? So there's possibilities for us for teams who have solutions and work on that, right? There's ways for us eventually throughout the competition that we can help you connect. We can do that, right? Eventually, as the competition evolves, we can help you connect with our partners, which then are potentially able to help you to develop your idea further. That makes sense?
Yeah, thank you very much.
Okay. Any further questions? You have been very active and asked many questions, which is wonderful. I truly hope that some of you we will continue this conversation after today's meeting, and I really hope that some conversations are now starting, and if you have questions, please reach out to me personally. I'm happy to answer more questions regarding topics I covered today, or even obviously how to join the competition, and really regarding like help you understand what else is part of being an XPRIZer for this XPRIZE quantum applications, and how networking works, and how we want to help teams to solve these challenging problems using quantum algorithms.
Okay, thank you very much, Kathrin.
Thank you.
In today, I mean, I'm sure there'll be a lot of several things coming up from this session for the competition.
I would love to see that too. Yes, please.
Yeah. Thank you all participants in today's sessions. we had an insightful discussion today. And thank you again, Kathrin, for sharing your expertise. So I hope this has broadened our understanding and from the beginning covering the applications of quantum computing and the price of as well.
Yeah, thank you.
Please take some time to review and practice the concepts that we had on YouTube. We pushed this video on YouTube so I can go back to fresh your mind and then also get the information that I was given out today. So we'll meet again next week. You have your content on my class, the virtual class, where you can go through your courses and also practice on the previous sessions. So we'll meet again next week, and next week we have some few. So bye-bye. Thank you again, Kathrin, for honoring our invitation.
Yeah, thank you for having me. That was wonderful, and good luck with everything. And I hope I will work with some of you soon. So thanks again. Take care.
Okay.
Bye.
Okay. Bye.
Bye.